Dr. Dotto will teach you about the item response theory. You have discussed the program schedule. I'm requesting, please you maintain the mute. Now it is okay.
Good morning, everyone. I hope I'm audible to all of you. Can you please confirm? Am I audible?
Yes, you are.
Yes, ma'am.
Yes, ma'am.
Okay, thank you so much. Just give me a minute. I'll just open my slides. So, how many of you are acquainted with item response theory?
Yeah, I know about it a little bit.
Okay, great. Great. Okay, so are the slides visible to all of you?
Yes.
Yes, ma'am.
Thank you. All right, so today I'm going to discuss item response theory, which is considered as an advanced approach in psychometrics. Okay, and okay, I hope the slides are moving and you all are able to see the content page, right?
Yes, it's working well.
All right. So I'll start with the limitations of classical test theory. I believe that in yesterday's class you got to know about the classical test theory, the basic principles. So I'll start with the limitations of classical test theory, and then I'll discuss the conceptual basis of rush measurement, how we can derive IRT from the principles of classical test theory, and then I'll discuss the item properties in IRT and the models, dichotomous and polytomous models in IRT, with some demonstrations in RStudio if time permits. Okay. So classical test theory, as you all know, um, that it actually deals with the combination of true score and random error, right? So when we are saying that it's the uh, true score and random error, it is basically what or how we are trying to explain the observed score. All right. So when we are actually measuring someone's score, any test you are giving and you are getting some score, it is basically the unweighted sum of the person's responses to the instrument's items. Okay. So in ability or achievement assessment, this sum reflects the number of correct responses. As simple as that. Now, this particular model, this classical test theory approach, basically relates the individual's observed score to his or her location on the latent variable. What is this latent variable? Something which you are measuring. Okay, it can be the intelligence, it can be some ability, some achievement, some particular aptitude. Okay, it can be someone's stress level, even whatever you are measuring, that is the latent variable. And uh, this observed score actually is indicating his or her location on this particular latent variable. Okay. So to understand this model, assume that an individual is administered an instrument an infinite independent number of times. So suppose you are taking one single individual and you are administering one single set of item to this particular person for an infinite number of times, means a large number of times, maybe 1 million or 10 million or 100 million times. Okay, so what will happen? Okay, at the end of all these administrations, we can calculate the person's observed score on the basis of the average of all these administrations. Okay, so you have administered it 1 million times, and then you get an average score, and that will indicate the person's observed score on that particular scale, right? But is it really possible to administer the same set of items to one individual 1 million times? Anyone? Is it possible?
No, ma'am.
Yes. No. All right. Why? Why is it not possible?
But the person will remember those things and then will give the response.
Yes. So there will be a lot of confounding variables in that case, right? And after a while, you will see that a lot of practice effects will come, and so that's why it is not practically possible. So that's why what we do is that instead of administering this one set of item to one single person for this infinite number of times, we administer the same set of items to an infinite number of individuals or a large number of individuals. Okay, so that we are able to find out that what is the average of this particular. Sorry, kindly mute yourself. Okay, if you are not responding, please mute, otherwise the class is getting disturbed. Okay. All right. So when we are administering the same set of items to this 1 million individuals, it is bound to happen that you will see that a lot of disturbances will come, and someone is well, someone is not well, someone is having a different mood. Okay, some other disturbances can be there in the testing situation. So all these actually causes uh, a lot of errors that we call that we refer to as the random error in this case. Okay, so this random error is nothing but these kind of disturbances, this kind of confounding effects that we see in the testing situation. Okay, so this observed score is not exactly the true score that we can get for a particular person based on his or her ability or achievement. It is basically a combination of this true score and the random error. Okay, and you will see that there is always a difference between this observed score and the mean score. Mean score means the average of all the individuals observed scores taken together. So this difference is actually considered to be the error. Okay, so that's the basis of your classical test theory approach, right? Now, when we are talking about the limitations, okay, let us consider this particular situation here. We have 3 different cups, all right, and we have a measurement scale on the left, as you can see, I hope. So what we are doing here is that, let us take, this is the base level, and if we consider the height of the first cup, it's 2 units. Okay, if we consider the height of the second cup, it's 3 units, right? And when we are considering the height of the third cup, it's 4 units, as you can see, right? Now, you see the difference of height between the first cup and the second cup is 1 unit, and the difference of height between the second cup and the third cup is also 1 unit. So can we say that the first cup and the third cup, if we consider the heights of these two, the first and the third, it's basically 2:1. This particular ratio can be considered? Yes or no?
Yes.
Yes, yes.
Yes. All right. So yes, it is correct. We can refer to it as a 2:1. If we are comparing the heights, and this is what we call the linearity of the measurement scale. Okay, something that we get in any physical measurement that we are doing. Okay, any physical measurement you are doing, you are getting some linearity there. But when we consider any psychological assessment, okay, then it becomes a problem. Okay, so the kind of complications that we face in psychometric assessment is that, firstly, there are a lot of errors that can exist in the measurement. Okay, some errors on which we do not have any control, right? We can just try to reduce the errors, but mostly there will be always these errors in a psychometric assessment. So these errors in measurements do exist. Again, in ability tests, all items do not have the same difficulty level. Okay, any ability test you consider, you will see that all the items will have different difficulty levels. Okay, now you consider this one single example here. Let us consider there is a latent trait which we are measuring, and the lowest score that can be obtained here is 0. The high score that can be obtained here is 30, right? So we have the first few items which are of low difficulty level. Then in the middle, we have a number of items which have average difficulty level. And in the final, last phase, we have a few items which are of high difficulty level, right? So what it means is that for solving these items of low difficulty, some low trait level is required. Someone who is with a very low trait level. Okay, suppose if it's an intelligence test, some intelligence will help the person to solve it because the items are of low difficulty level. Okay, and of course for the average difficulty level items, you need to have average trait level. So trait level should be average, and for high difficulty level, higher trait level is required. Okay, now you consider 4 different persons. We have Manas, who got a score of 4, suppose, total score. We have Charu, who got a total score of 12. We have Robin, who got a total score of 20. And we have Jaya, who got a total score of 28. Now, what is the difference of score between Manas and Charu? Anyone?
24. Manas and Charu, 8.
Manas and Charu, 8.
8.
Right. Right. Charu and Robin, 8.
8.
Again.
8.
And Robin and Jaya, again.
8 also.
8. Right. So these are the observed differences. Right. So if we are just looking at the scores, these observed scores, someone can say, considering the linearity in measurement, someone can say that the difference of trait level between Manas and Charu is the same as the difference in trait level between Robin and Jaya. Okay, so if it's a test of intelligence, suppose the difference of intelligence between Manas and Charu is the same as the difference in intelligence between Robin and Jaya. Can we say that? Is this statement
Ma'am,
correct?
number wise it is same, but if you go with difficulty level,
Right.
with difficulty
Right.
level it is no.
Absolutely.
Not
So if
linear.
you're considering just the observed scores as we do in classical test theory, then we are actually coming to a wrong conclusion, isn't it? Because we are saying that it's the same, the difference is the same difference in trait level, but it is actually not. Why? Because Manas, getting a score of 4 means that Manas was able to solve only few items which were of low difficulty level. So the trait level of Manas is very low, intelligence is low. Charu could complete, all the items of low difficulty level and maybe one or two items of the average trait level. Okay, so maybe Charu is actually coming into the average level. Robin is also coming into the average level because Robin is able to solve mostly the low difficulty items and the average difficulty items. But Jaya getting a score of 28 means that Jaya actually was able to solve all the items of low difficulty level, average difficulty level, and most of the items in the high difficulty level as well. Okay, so as per the trait level, these 4 people are not the same, and we cannot really consider this linearity in measurement when we are trying to compare the trait level. Okay, so it becomes difficult to compare the ability level based on the raw scores, which we actually do in the classical test theory approach. Okay, I give you another example. Let us consider the big depression inventory. So we have, in this particular scale, we have all these different items. And for each of these items, you see that, for example, the first one, there are 4 options. 0 stands for I do not feel sad. 1 stands for I feel sad. 2 stands for I'm sad all the time and I can't snap out of it. And 3 stands for I'm so sad and unhappy that I can't stand it. Okay. Now, when we are, going by the classical test theory approach, what we are doing is that we are just considering the observed score. So someone who is getting a score of say 3 in the first item and again a score of 3 in the 7th item, we are considering all these to be the same because it's just a difference of numbers that we are considering. Okay, or someone who is getting a score of 0 and someone who is getting a score of 1. Okay, we are taking the difference to be 1 unit. Again, someone who is getting a score of 2 or 3 in a particular item, again, we are considering it to be a difference of 1 unit, but it is actually not. Okay, so this traditional method of scoring actually assumes that each item or symptom on the scale represents comparable level of trait or severity. Okay, also it assumes that each item has identical properties across samples. When you are administering the BDI to all these different population, we know that it's a very popular scale, and so we are able to administer it to people across the world, right? So CTT approach assumes that all these items has identical properties across all samples, but it is actually not, because we know that it can be very culture specific. Cultural factors might be affecting the responses of individuals. Okay, and it is definitely going to differ across different cultures. Again, 2 individuals having the same score can differ in terms of relative severity and frequency of different components of psychopathology. How so? for you just consider two people having getting a score of 30, right? Both of them getting a score of 30. Now we have an item here, item number 9, which talks about the suicidal ideation. Okay, so maybe the first person chose the fourth option, that is, I would kill myself if I had the chance. Okay, and got a score of 3 here. Okay, and maybe the second person did not choose this particular option. Okay, but overall, when you are just looking at the observed score for these two people, you are you know assuming that both of them, they are having the same severity level, but actually one of them is having depression with suicidal ideation, and the other person is not having that much level of suicidal ideation. So how do you um, uh, make a diagnosis based on this differences that you see here, right? Again, distance between I don't feel disappointed in myself and I am disappointed in myself is not the same as the distance between I am disgusted with myself and I hate myself. So if we are assuming linearity in measurement, then these are taken to be the same, but these are actually not the same, because all these options are actually showing or representing different levels of severity. So these are some of the complications that we face, and actually psychometricians around the world, they faced when we had only the classical test theory approach. Okay, so I'll come to the um, Gutman structure, which was proposed after the classical test theory, the limitations of classical test theory were focused, and people started, researchers, psychometricians, they started discussing about the limitations of classical test theory. Then at that time, Gutman structure was proposed. Okay, so what is this Gutman structure? See, let us just consider this hypothetical example where you have all these items, okay, till item number 8. So there are 8 items, and there are 7 people who answered all these 8 items, right? Now let's see what each of these people, they scored for themselves. The first person got a score of 4. This person got the item 1, 2 and 3 correct, and then item 6 correct. Okay, the others are wrong. For person 2, the first 3 items were correct, fourth item was wrong, and then the next 3 items were also correct. Okay, so he or she got a score of 6, and likewise all the other people also scored in that way. For but you see one thing, that total score being same for person number 1 and person number 3, both of them got a score of 4, but the specific items which were answered correctly by person number 1 were not the same as those answered by person number 3. Okay, so each of them got 4 answers correct, but which of these items got correct were not the same. Okay, the same thing is true for person number 5 and 7, and again person number 4 and 6. Okay, so this is how we get the data in the real situation when we are administering a set of items to a number of individuals. This is what we actually get, right? Now, as we know, the classical test theory assumes that the total score is the sound summary of the responses, right? So we are just looking at the total score and we are saying that, okay, this person is having this much level of trait or this much level of severity, like that. So this follows that the theoretical correlations among items are positive and the same. But in real data, it is not followed due to sampling variation. In real data, what happens is that we get lot of random error because of sampling variations. Okay, you get data from different backgrounds, people from different backgrounds, different cultural backgrounds, and there are many other demographic factors which might be affecting. Okay, so due to all these sampling variations, what happens is that we do not get any specific pattern in the responses. Okay, and this sampling variation produces a lot of error. So as this error component goes up, okay, what will happen? The observed score will be inflated, right? So it will be affected, because we know that in classical test theory approach, observed score is actually the summation of true score and random error, right? So for a total score to be used to summarize the responses of items on an instrument, it is necessary that the inter-item correlations and therefore item total correlations are positive and homogeneous. What are these item total correlation? These actually tells us that whether all the items are measuring the same particular latent variable or not, right? So if we find that all these item total correlations are not positive, or they are not homogeneous, meaning that they are not similar, then it becomes, a huge problem when we are trying to interpret the scores. So from the perspective of classical test theory, it is perfectly reasonable to have all the items more or less of the same relative difficulty, right? Now, what happens here in the, when Guttman structure was proposed, it was argued that the following criteria must be met before the scores on the items could be summed to get a meaningful single score for a person. So when we are considering the observed score to be the, representing the trait for a particular person, based on one single score we are concluding, then this particular criteria must be met. What is this criteria? If person A has a greater total score than person B on a test, then person A should have answered all the items correctly that person B has answered correctly, and in addition, some other items that are more difficult. Okay, what does it mean? You consider this example here. We have again 6 different persons who answered 5 different items, right? So just take a look into, how each of these people, they fared in this particular testing. First person got all the items wrong. Okay, so the total score is 0. Second person got a score of 1. But actually, if you look at it, which particular item was answered correctly by the second person? Item number 1. Okay. Third person got a score of 2. And how is it answered? First item got correct, and then second item got correct, right? Likewise, as you go down, you see, as the scores are increasing, just, it is following a very regular pattern in which the next person is answering all the answers correctly answered by the previous person, and then one single extra. So the 6th person has answered all the items correctly. So, that person has got a score of 5, total score of 5. Okay. So again, if you look at the, last row, you'll see that the first item was answered correctly by 5 people. Second item answered correctly by 4 people. Third item answered correctly by 3 people. Okay. And likewise. So this is the perfect Guttman structure that was proposed. Okay. Now tell me whether this perfect Guttman structure that we are looking at, is it possible in real life situation? Anyone?
No, ma'am.
No.
No.
Correct. Right. So what happens here is that cases where items do have different difficulties, positive correlations among items imply more or less that persons with the same total score will tend to obtain similar scores on the same items. Okay. For example, in a test of proficiency with items of different difficulty, in which 2 persons with the same total score have very different patterns, it would imply that one person has answered some more difficult items correctly compared to the other person, and vice versa. Hence, it is not justifiable that these 2 persons have the same proficiency. So we can be looking at the same total score obtained by 2 people, but it does not really mean that the 2 persons will have the same proficiency on that particular test, right? So This Gutman structure, was later on rejected because of this, hypothetical structure that it proposed, because we know that in real life situation, in real data, this does not happen. Okay, so that is fine, but the main contribution of Gutman structure is that it provided a tangible interpretation of a continuum, okay, and an understanding of what more or less on the continuum means. Before this, when we, earlier, when only the classical test theory approach was being followed in psychometric test construction, the main problem was that people had no idea about how to conceptualize this continuum, okay, in testing situations, okay. But after Gutman proposed this particular structure, Gutman structure, it is of no use in real life situation. But the only thing that mattered was that after this, people were able to, psychometricians were able to form a tangible interpretation of the continuum, what it actually means. Okay, so this Rush model of measurement actually was derived from this Gutman structure. So it actually formed a bridge between the classical test theory approach and the IRT approach. Okay. So Rush model, as we know, Rush model was the first IRT model that was proposed back in, I think, 1960s. It was proposed. So Rush was the one who proposed this Rush model of measurement, and um, it actually followed, it is not something that is completely different from classical test theory approach. It is actually something which is related to CTT. Okay, so what happens here is that when we are looking at the discrimination index in classical test theory, all of you are acquainted with discrimination index? Yes, in classical test theory?
Yes, ma'am.
All right. So what is this? It is the correlation between the score on an item and the total score on the test. Okay. So basically the item total correlation that we can consider as a measure of the discrimination index in classical test theory approach. Also, there is another way of calculating this DI. Okay, where what we do is that we divide this entire number of people into 3 different groups based on their total score, namely the lower third, the middle third, and the upper third. So just consider this example here. I hope all of you are able to see this example. There is this question. The capital of Madhya Pradesh is, options are Jabalpur, Indore, Bhopal, and Raipur, right? What is the correct answer here?
Bhopal.
Bhopal. Right, very good. So you see that let us suppose the total number of respondents who answered the items correctly, answered the item is 120. So, for calculating discrimination index, we have to divide this 120 individuals into 2 categories. So the upper category consists of 40 people, and the lower category consists of 40 people, and the middle category also consists of 40 people. So for calculating DI, we do not have to consider the middle category. We just consider the upper and the lower one. Now you see that distribution of people answering the item correctly, or choosing each of these options, in the upper and the lower group. So the first option, Jabalpur, was selected by one person in the upper group. Upper group means some people who got a higher score, so they have a higher ability. And the lower group means those who are having lower ability, who got lower scores in the test. Okay, so for the first option was selected by one person in the upper group and 8 persons in the lower group, right? Second option, Indore, was selected by 2 people in the upper group and 15 people in the lower group. The third option, the Bhopal, that is the correct option, was selected by 36 people in the upper group and 7 people in the lower group. And finally, the D option, Raipur, was selected by 1 person in the upper group and 10 persons in the lower group. Right? Now, what do we see here? For calculating DI, we have to consider those who selected the correct option in the upper group minus number of people who selected the correct option in the lower group divided by total number of people in each of these groups. So that's how we are getting a score of 0.725, which is the discrimination index of a particular item, right? So that's how we calculate the discrimination index in classical test theory approach, right? I hope that all of you are acquainted with this part, correct?
Yes, ma'am.
Okay. Now consider this, okay? Let us consider this particular graph here. So in the x-axis, we have this lower, middle, and upper group that we just discussed, okay? And on the y-axis, we have proportion correct. How many of these people got it correct? Okay, in the lower group, in the middle group, and in the upper group. And we have 4 different items shown here. Okay, item 1, 2, 3, 4. Can anyone tell me which is the easiest item among all these? Anyone?
The blue one.
Item 1.
Item 1. All of you agree?
Yes.
Yes. Correct. So why item 1? Because item 1 is answered correctly by
Most of
yes,
the participants.
90%. Right. 90% of people in the lower group, almost 92-3% in the middle group, and almost 100% in the upper group. Okay. And which of these is the most difficult one?
Item 4.
Item 4.
Item 4. Correct.
Item 4.
Right? Because no one in the lower group could answer it. Okay, 20 or 30% in the middle group could answer it, and in the upper group, around 55 to 60% could answer, right? So this is how we are going to, represent each of these items, as per the group means of these different lower, middle, and upper group of people, right? Now, consider more than 3 class intervals. Okay, here we had 3 class intervals, the lower group, the middle group, and the upper group. Now let us consider that, suppose in a particular assessment, there were large number of people around, like 10,000 people answered number of items, around, say, for example, there were 18 items which were answered by this 10,000 people, and all of them got some total score, right? So since there were like 10,000 people in that particular testing, it is possible that one particular observed score was obtained by thousands of people, right? So maybe 2,000 people obtained a score of 3 out of 18, and then 5,000 people obtained a score of 2 out of 18. Okay, so in that case, when we are plotting the same thing in this way, where we are getting this proportion of correct on the y-axis and the group means in the x-axis, if we are plotting the same thing for 10,000 people for 18 items, okay, it is possible that we are going to have something like this. Okay, so you see it's the same thing. In the x-axis, you have all the possible total scores. So we have the lowest possible score is 0, and the highest possible score is 18, right? Because there are 89. And since there are 10,000 people answering all these 18 items, it's possible that hundreds or thousands of people obtain one single score that is maybe a score of 9 obtained by 2,000 people, or obtained score of 10 obtained by 1,000 people, and so on. Okay, so you get 18 different categories of responses based on the total score. Is it making sense to all of you? Are you all able to? Yes? Making sense? Okay, let me explain it again, right? So it's the same thing that we are plotting, but since you have 10,000 people answering the same number of questions, so for each particular score on this 18 item test, you are going to get thousands of responses. Okay, so it is possible that item number 4 was, or the total score of 4 was obtained by 500 people. Then a total score of 5 was obtained by 700 people. Okay, total score of 8 was obtained by 1000 people. Okay, so in that way, if you are plotting the responses of these 10,000 individuals here, okay, and you are trying to calculate the proportion of positive responses, you are going to get something like this. This looks like this. Okay, is it clear to all of you?
Yes, ma'am.
Ma'am.
Okay. So now let us consider these 4 items, item number 3, 7, 11, and 15. Can anyone tell me which is the easiest item of all these 4?
Item 3.
Item 3, right? Yes, correct. Why? Because you see that all these people, those who got a total score of 1, okay, out of 18, maybe 300, 500 people, or maybe more than that, maybe 8,000, 10,000 people, whatever it is. Okay, so all these people who got a total score of 1, probably it will be a little lower than the others, 300 or 400 people. They were also, among them also, around 20% of all those people could answer item number, not 20%, actually 40% could answer the item number 3 correctly, right? So that's how it goes. And you see that almost 100% of people could answer item number 3 correctly, among that particular group, which is who got a total score of 11 or 12. Okay, so all those people, maybe 5,000 people or 4,000 people who got a total score of 12, all of them could answer item number 3 correctly. So basically it shows that it is of very low difficulty level, right? And so it is located on the left side of this continuum. Okay, this x-axis is actually the continuum that we are considering, continuum of possible total scores. Okay, and as you go towards the right, you are getting higher scores, indicating that people having higher level of that particular ability or trait will be located on the right hand side. Correct? So all those items which are of low difficulty level will be located on the left hand side. That's what we are seeing here, right? And the most difficult item here is item number 15, right? Yeah.
Yes.
Yes, correct. So why? Because you see that only those who got 18 out of 18 could get the item number 15 correct, right? And mostly people got it wrong, mostly. All right, so that's how we represent this, for this infinite number of people here. Now, if this continuum is abstracted to true scores, here we are considering only the total scores. Okay, now you assume that we are not considering the total score, we are considering this to be the true scores. Then the proportions are theoretical, that is, they become the probabilities. Okay, these are probabilities that a person of a given true score will respond positively to an item of particular difficulty. So instead of the total score, the true score is located on the horizontal axis. And instead of the observed proportion of persons with a positive response, the probability of a positive response is plotted on the vertical axis. This is only possible when you are considering an infinite number of people for your testing. So then it looks something like this. So this x-axis, which was previously the total score, possible total score we were referring to, now it becomes the true score in classical test theory approach, or it is also the, we can consider it to be the person location. And as I was mentioning, that as you go towards the right hand side, you have you need to have a higher true score as per the classical test theory approach to answer those items correctly, right? So it means this x-axis is the continuum which actually helps us identify the location of a person and also location of an item. So those items which are located towards the right hand side, those are the difficult ones, and those which are located on the left hand side, like item 3, okay, they are the easier ones. Okay, and it means what? People who are located on the left hand side, they have lower trait level, and those who are located on the right hand side, they have a higher trait level, right? And on the y-axis, we get the probability of a positive response. Okay. So here comes the Rush model of measurement. Okay. So this Rush model of measurement, this, whatever we just discussed is the basis of this Rush model of measurement. And therefore, the Rush model of measurement is actually a probabilistic model. Okay. It is based on probabilities. So what is this probability? It can be considered a theoretical abstraction of an observed proportion. Okay. We talked about the observed proportion in the previous examples. Okay. When we are considering the theoretical abstraction of this observed proportion, these become the probability. So this modern test theory models, means the IRT models, they focus on the engagement of a person with an item rather than upon the total test score of a person, as in the classical test theory approach, right? So in classical test theory, we consider the total score as the representation of a person's trait level. But in IRT models, we focus on the interaction between the person and the item rather than the total score of the person. So here, Rush actually talked about two-way frame of reference. What does it mean? Talks about the kind or class of items which are governed by the construct being assessed. Whatever construct you are assessing, it can be intelligence, it can be depression, it can be anxiety, it can be self-efficacy, achievement, whatever you consider. All those items which you are including in your testing. Number 2, the second important part is the class of persons who are relevant to be assessed, whom you are actually assessing in your testing. And finally, the conditions of the administration of the instrument. So if you are trying to graphically represent it, it looks something like this. So in the if you look at the row wise, okay, you are getting an agent, considering the location of items, which is represented by delta I, as per the Rush model. And when you are looking column wise, it's the location of persons, which is denoted by beta, okay, beta n. And this xni, x is the response. So xni means the response of any person to any particular item is actually a function of this location of the person and location of the item, right? So as you consider the location of items, suppose you have a number of items, A1, A2, A3, all these are items which are located on the continuum, right? And you have the location of persons, person 1, person 2, person 3, like that. So this response, okay, when you are considering the interaction of the first person, that is O1, with the first item A1, you get a response of X11. Okay, so this response is a function of this person's location and the item's location. That's what it means. So this X and I, okay, or a response of one particular person or any person on any particular item is actually a function of the location of that particular person and that particular item on the continuum. Right? Is it making sense to all of you? Are you able to understand?
Yes.
Okay, please feel free to tell me if you have any doubt anywhere. Okay. So this frame of reference is also specified in classical test theory approach, although there the specification is in terms of population. There the instrument should be relevant for the population of persons who are to respond to the items. So conceptually in classical test theory approach, an instrument is applied to a random sample from the population. Likewise, the items are seen to be the sample of items from a population or universe of items, where in principle, each item is a replication of all other items. But in classical test theory, there is no item location parameter such as its difficulty. There, by the term item difficulty, we mean that what is the difficulty level of the item, that's it. But in item response theory, rush model, it is not just the difficulty level of an item. Okay, this actually indicates the location of an item on the particular continuum. What is this continuum? Continuum, the concept of continuum was given by the Guttman structure. Okay, so the Guttman structure elaborates classical test theory by implying a relative location of the item where their differences in location are central to understanding the variable. In Rush's two-way frame of reference, each person and each item has a location parameter specified. So we have the location of an item, we have the location of a person. Because the items are intended to assess the same variable, there is of course a sense in which the items are replications of each other, as in classical test theory. So, this Rush model, this Rush's two-way frame of reference is not something that is completely, which came out of the blue. Okay, as you can see, it can be very easily derived from the classical test theory approach and the concepts of Guttman structure. So both the classical test theory and the Guttman structure actually contributed into the development of this Rush's model of measurement. Okay, so if we are trying to build this Rush model from these parameters, we know that Rush model is a probabilistic model. So how do we build it? Let us consider the response of person N to item I is denoted by X and I, as we just discussed. And in the dichotomous response case, it takes on only values X and I is equal to 0 or X and I is equal to 1. X and I is equal to 0 means the person got the item wrong. And X and I is equal to 1 means the person got it correct. Right? So in dichotomous response cases, dichotomous response means yes or no, either correct or incorrect. Right? So the X and I, or the response of any one particular person to a particular item, can be either 0 or 1. Isn't it? Is it making sense to all of you? X
Yes,
and I,
Yes. Yes, sir.
either 0 or 1. So these parameters.
Ma'am, please repeat 1 second, please, ma'am.
I'm not able
I
to
can't
hear
got
you.
it. Ma'am, please repeat. I can't got the point, ma'am.
Okay, let me explain it again. Okay. So this X and I basically indicates the response to a particular item, right? Clear? Any response to a particular item? Now, when we are considering a dichotomous item, okay, dichotomous item means
Yes or no.
binary. 1. Either 0 or 1. It will be either correct or incorrect. There is one correct answer. Right? So what can be the value of this response? Either 0 or 1. If the person gets it correct, he or she gets a score of 1. If the person gets it wrong, then he or she gets a score of 0. Isn't it? Clear? Everyone?
Yes, ma'am.
Okay. Now, these parameters, beta n and delta I, can take on any real values. Why? Because this item or the person's trait level, the difficulty level of the item or the person's trait level can take on any real values, which can be, ranging between minus infinity to plus infinity. So if comparisons are to be made between persons in terms of their parameters and between items in terms of their parameters within a frame of reference, then the structure of the responses should be such that, number one, comparison between any two persons is independent of which subset of items in the frame of reference is chosen for making that comparison, and independent of any other persons that might be compared. Number one. And number two, comparison between any two items is independent of which subset of persons in the frame of reference is chosen for making the comparison, and independent of any other items that might be compared. Right? What does it mean? It might sound a little confusing to you. Let us just consider this, visual representation here. So these are the continuums. These straight lines which you are seeing on the left-hand side of the slide, these are the continuum, straight continuum, okay, that we are considering. Now, just in the previous slide, as we discussed, the location of a person and the location of an item on a particular continuum. So what you are seeing here is that the beta is actually indicating the location of a person on the continuum, and all the delta that you are able to see are indicating the location of items on the continuum. Now, when person n responds to item I, which is scored dichotomously as positive or negative, so the person gets a score of 0 or 1, the person's response x and I is a function of the person's location beta n and the item's location delta I. What does it mean? Let us consider the first example. You are seeing the continuum and there are a number of items and one person. So the location of beta indicates the location of the person on the continuum, and the delta 1, delta 2, delta 3, delta 4, and delta 5 indicates the location of 5 items on the continuum. Right? Can anyone tell me how many items can this person get correct in this first example out of these 5 items? How many can he or she get correct?
3. On the first item, he got a score of 3.
3. So the first 3 items are answered correctly, right?
Yes.
Making sense to all of you? All of you able to understand?
Yes, this is clear.
Right. Now consider the second one. How many items will the person get correct?
0.
0. Right. What about the others? Are you all able to understand?
Yes, ma'am.
Okay. Let us consider item number 7. Example number 7. Okay, not item, the 7th example. Okay. So we have here 2 people. You are comparing 2 people, the first person and the second person, beta 1, beta 2. And we have 5 items. Okay, delta 1, 2, 3, 4, 5. Who is having more trait level among beta 1 and beta 2? These 2 people?
Beta 1.
Beta 1.
Beta 1. Correct. right? You see, but if you consider only the observed score here, both of them will be getting the same score.
Yes.
Right? Out of these 5 items, beta 1 got the first 2 items correct. Beta 2 also got the first 2 items correct. Right? So observed score for these 2 people will be 2 out of 5. But if you consider the location of these 2 people on the continuum, the first person is located way ahead of the second person. Got it?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Okay, so that's what the Rush's model actually considers. Whenever we are trying to compare 2 items, okay, the Rush's model assumes that if we are actually, placing all these items on the continuum, then you can compare any 2 items irrespective of any other factors. Doesn't matter, whom you are actually giving. In classical test theory approach, the problem that we face is that you get, suppose you consider a set of 10 items and you go and administer it to a class of children who are coming from a good school, suppose. Okay, there are 100 children who are from a good school, who get good results and all, and then on the basis of their responses you calculate the difficulty index, right? What will you find? You will find that most of the items will be answered correctly by all these 100 children. So for them it's an easy set of items. But you take the same set of item and go to another school, administer to another 100 children who are coming from maybe a municipality school, and not who do not really do well in their studies, and then you calculate the difficulty index, you will see that most of them, they are not able to answer the items correctly, and that's why this set of items becomes difficult for them. So what will you conclude? Are your items easy for all these children or difficult for all these children? How will you generalize to the population? Because it becomes dependent on the sample to which you are administering it, right? But when you are placing all these items on a continuum and you are trying to compare individuals or items on the basis of this continuum only, then it doesn't matter whom you are giving the item, because you are comparing their true score, you are not comparing their total score. Okay, so it's the biggest advantage of the Rush's model, that we are able to compare any 2 item, any number of items actually directly on the basis of their location parameter on the continuum. Okay, irrespective of the sample to which you are administering these items, and also we are able to compare 2 different individuals directly, coming from any background, gender, educational background, cultural background, anything. You do not have to be worried about any of those things. You can directly compare them, because you are placing them on the trait level and you are comparing the true score, not the observed score. Clear, everyone?
Yes, ma'am.
Yes, ma'am.
Okay. So now just quickly, I'll just tell you how, from all these things that we discussed, how we actually derive the equation that we have for Rush's model. So if the person's proficiency is greater than the item's difficulty, we would expect the probability of a correct response to be greater than 0.5. That is, if beta n minus delta I, that's the difference between the item's location and the person's location and the item's location, if it is more than 0, then the probability of giving a correct response is higher, more than 0.5. So means that if the person's ability level is more than the item's difficulty level, then the person is definitely going to give a correct response, right? Likewise, if the person's proficiency is less than the item's difficulty, then we would expect the probability of a correct response to be less than 0.5. So means that if the item is more difficult for a particular person, then it is more likely that the person will give a wrong answer. So the probability of giving a correct response is less than 0.5. It follows that in the case where the person's proficiency and the item's difficulty are identical, that the probability of a correct response would be 0.5. That is, if beta n minus delta I is equal to 0, then probability of a correct response is 0.5. This analysis allows to relate the probability of a correct response to the difference between the person's proficiency and the item's difficulty. Probability can range from 0 to 1. As we know, mathematically, probability can be anything between 0 and 1. The difference between the proficiency and the difficulty can range from minus infinity to plus infinity. So in that way, the probability of giving a correct response can range between 0 and 1, and the difference between the person and the item's location can range between minus infinity to plus infinity. So in a further transformation, if we transform the difference between this proficiency and difficulty using it as an exponent of the base e, the expression will have the limits of 0 and infinity. So then, it looks something like this. With the further transformation, we can obtain an expression which has the limits 0 and 1. Therefore, can be the probability of a correct response. The expression and its limits are this e to the power beta n minus delta I by 1 plus e to the power beta n minus delta I. This, it ranges from 0 to 1. So if we take this formula to be the probability of a correct response for person n on item I, relationship can be written as probability of correct response, giving a correct response, given the person's location and the item's location to be beta n and delta I, is equal to e to the power beta n minus delta I by 1 plus e to the power beta n minus delta I. So this is the standard equation that you will see everywhere, which is actually denoting the dichotomous Rush model. Okay, so don't worry about the mathematical expressions. It's just as we go through, as we discussed all these basic conceptual background of how we can derive this Rush's model from the classical test theory and the Guttman structure. So mathematically, how you can come to this equation, which was ultimately proposed by Rush in the 1960s, and it is actually considered to be the first step, first IRT model in advanced psychometrics. Okay, so it's a mathematical model for dichotomous responses, and for measurement based upon right or wrong answer, difficulty level of the item must be considered. And Rush's model assumed that when a respondent answers an item, this relationship is expressed by the natural log of the respondent correctly answering the item divided by the probability of the respondent not correctly answering the test item. So here, two important aspects are there. The first is location of the test item along the trait level, and number two is location of the respondent along the trait level. So this one allows researchers to use a respondent's raw test score or scale scores and express the respondent's performance on a linear scale that accounts for the unequal difficulties across all test items. So remember the first thing that we started with this lecture, the example of the cups. Okay, and we talked about how the linearity of measurement is possible in physical measurement, but not in psychological measurement if you're considering the classical test theory approach. Well, the Rush's model actually provided a mathematical model based on which we can directly compare the psychological trait of two people if we are considering the location of the person and the location of the item together on the continuum. So that's the solution to the limitations of the classical test theory approach. And that's why Rush's model actually became very popular at a later stage. And, subsequently, many different other IRT models were proposed at a later stage. Okay. So I hope this much is clear to all of you. Any question till here?
Yes, ma'am. I have a question regarding the graphical representation. So
Yes.
before we normalize the graphical representation, can is there any development, or can we divide the responses by dropping a horizontal perpendicular and a vertical perpendicular from like from point 0.5 and point 0.5, and then develop the model into traits like uh, low trait and high trait on the like in the quadrants, like the lower quadrant, low
Yeah,
trait,
yeah,
high
I
trait,
got it.
high trait, high trait, low and
Mhm.
high trait, and then high and low trait. So
Yes,
something like that
yes,
to get.
yes,
I don't know
yes,
if my
yes.
question is clear or not.
No, no, I got your point. Yes, that is exactly what we do in IRT. Okay, when we are trying to locate the, find the location of a particular item on the scale, you have to actually drop a perpendicular, vertical perpendicular from the point 0.5 level for each item on the x-axis, and that actually indicates the location of a particular item. That is something that I'm going to explain in the next slide. Okay, so yeah, that's how it is denoted in the IRT. So in the classical test theory, we do not do that, but mathematically, when we are deriving the the Russia's model from the test score and the theoretical, we are actually making a theoretical abstraction of the real problem. Then of course we have to do it in order to find the location of the item on a particular continuum. Clear?
Yes, ma'am.
Okay. Any other question or doubt?
Yeah, ma'am. I have one question.
Yes.
Ma'am, if I administer a test and I put all my difficulty equal, so can I calibrate that test using the CTT?
You can do that. Of course, you can do that. But the
Is it
problem here
reliable?
is that in no, that is the problem. It is not considered reliable anymore. Like 50 years back, if you would have done that, people would have accepted it. But now if you are trying to develop a test and you are doing this classical test theory approach for calculating the difficulty levels, no one is going to accept it, because it is not considered reliable anymore. Okay, although if you are taking proper precautions and you are considering a good sample, good representative sample for your testing purpose, then you will find that IRT and classical test theory will give you comparable results. Okay, but of course you have to go for IRT to uh, provide a confirmation of whatever you have. Like classical test theory can actually give you a hunch about which of the item is not working properly, but it does not give you clear information, reliable information about which item you should be retaining, which item you should be rejecting. Okay, so for that you have to go for IRT.
Okay.
Okay,
One
does that
more
answer
question.
you?
Yes, ma'am. I have one more question.
Yes.
Can we use logistic distribution in place of RAS model to,
Logistic what?
ma'am,
Regression?
logistic distribution in place of RAS model
Logistic?
to
Uh,
get the probability
see
of
the
correctness?
yeah, yeah. See, the that is also a logistic model that we are going to discuss now. Okay, this rush model that we are talking about, it is also a logistic model only that we are going to discuss, because it is definitely the basic assumption that the first model, the rushes model that was developed on dichotomous responses. Okay, so the basic assumption is that you have two different categories of responses, and then how you are going to treat all those responses for your item. So it is going to be a logistic model only.
Okay, ma'am.
Okay, I hope I'm share হয়ে আছে, so internet connection unstable বলছে। Okay, can anyone confirm that if I'm audible, and are you all able to see the slides?
Yes, ma'am.
Okay, okay. So we are going ahead then, right?
Ma'am, I have posted a question in chat box. Sorry, I wasn't able to unmute myself. Ma'am, what if we have more than two options in a question, ma'am?
Okay,
So
okay,
which,
okay. I just answered it. I think the network connection was gone, so that's why you couldn't hear.
okay.
In such cases, we use polytomous IRT models. I'm going to discuss that in
Okay.
the next slides. Okay.
Okay. Thank you, ma'am.
Okay. Yeah. So there are a number of assumptions of IRT. These are the four main assumptions of IRT. Monotonicity. What is this? The first assumption, as the trait level increases, so does the probability of endorsing an item. Means what? Trait level increases means on the x-axis, if you are going towards the right hand side, okay. On the y-axis, you are going up actually. So people who are having a higher trait level, they have a higher probability of endorsing an item, and vice versa. So this is actually expressed as an S-shaped curve between the latent trait level and the probability of response to the item concerned. Okay. Second assumption is invariance, which means that invariance in ability level and item properties across different samples. Something that we just discussed, okay, that when you are actually administering all these items to different groups of people coming from different backgrounds or other different demographic backgrounds, we do not want any kind of variation in the responses because of their backgrounds, demographic backgrounds. Okay, so IRT assumes that there is an invariance in the ability level and item properties across different samples. So item properties measured in the same in particular sample remain indifferent to sample characteristics like age, sex, etc. Okay. Third assumption is the unidimensionality. It means that IRT assumes that all the items are measuring a single latent variable, right? So when you are trying to fit an IRT model on a set of items, say there are 20 items, okay, or 30 items or 50 items, whatever, IRT will assume that all these 20 or 30 items are measuring the same single dimension. Okay. So what to do if you have multiple dimensions? Say, for example, in a personality test, you have 5 different dimensions. Or an intelligence scale, you have like 7 or 10 different dimensions. What will you do then? Okay, in such a case, you have to go by the assumptions of IRT, and either you have to go for a dimension-wise IRT fitting, so you can fit the IRT model to one single dimension at a time, or you can take all those dimensions together and fit a multi-dimensional IRT model on all those dimensions taken together. You can do any of this, but of course, multi-dimensional IRT is much more complicated. So it is better to go for applying the IRT model or fitting the IRT model on one single dimension at a time. Okay, otherwise you will be violating the assumptions of IRT and you will have erroneous results. Okay. The fourth assumption is that of local independence, means that responses are independent. Okay, so item responses are uncorrelated after controlling for latent trait. So if you take out the latent trait part, okay, anything that is related to the latent trait part, if you are taking it out, the item responses should be uncorrelated to each other. So what happens here is that if there is some local dependence, okay, then this particular assumption is violated, and it distorts the item parameter estimates, causes the scales to look more precise than they really are, and a large correlation between two or more items can be essentially define or dominate the latent trait, thus causing the scale to lack the construct validity. Okay, so if you have a number of items having too much of correlation among them, okay, after even controlling for the latent trait, then what will you see? It becomes possible, it happens if you have like 2-3 items measuring almost the same thing in a particular test or scale. There it can happen that if all these items are measuring the same thing, so there is some redundancy in the responses you will see. Okay, and there even if you are taking out the latent trait, the items will be exhibiting local dependence among each other, and you will see that this correlation among this number of items will actually tend to dominate the entire scale. And you will think that, okay, you will have a very good reliability, and you will think that, okay, this scale is a very good one. Okay, it is it's a very standardized, a very well developed scale, but it is actually not. Okay, so these are some of the assumptions, 4 assumptions of IRT model. So this first one, monotonicity, this S-shaped curve that we talked about, this is the main assumptions of IRT, and this actually indicates, in IRT, the best part is that you can represent each and every item using an S-shaped curve like this. Okay, and it will tell you how the item is behaving. What are the difficulty level? What are the discrimination index? What is the guessing parameter? How the item is behaving, where the item is located, how it is differentiating or discriminating among people. All those information you can get from this one single curve, that is the S-shaped curve. Okay, so why is that an S-shaped curve? Because as per the monotonicity assumption of IRT model, what you are seeing here is that in the x-axis, you have an increasing, level of trait. Okay, whatever here it is like an achievement index, suppose. So we denote the x-axis as the theta level in IRT model. So in this theta level indicates that as you go towards the right hand side, it means that you have a higher trait level, okay, higher achievement. Okay, and in the y-axis, it is denoting the probability of correct response. So people who are having a higher achievement level, it is possible that their probability of giving a correct response is way higher than those who are having a lower achievement level. So that is being indicated by this S-shaped curve, right? Now, by looking at this S-shaped curve, we can actually try to understand the different parameters of the item. So for a dichotomous items, we have 3 different parameters: the difficulty level, the discrimination level, and the guessing parameter, right? So here, if we are drawing, the probability of correct response being 0.5, if we are assuming it to be 0.5, because 0.5 gives us the maximum variation in response. So we are assuming that the probability of giving a correct response being 0.5 or more than that. Okay, if we are considering that point and drawing a perpendicular on the x-axis, then what we are getting is the item location. Means what? This much amount of ability or trait is required to solve this particular item. Okay, so it means that this difficulty that you are seeing here, difficulty being 0.5, it shows that this any item of difficulty level 0.5 will be located on the trait level here. Okay, so let me just try to find the, yeah. Yeah, so I hope the spotlight is visible to all of you. So we are drawing this line, okay, this horizontal line from 0.5 level on the slope of this item, S-shaped curve. And if you are drawing this perpendicular on the x-axis, this particular region here shows us the location of an item on the trait level, the theta level. Okay, so this theta level, actually represents the trait level ranging generally from -4 to +4. Okay, and it means that this item is located here. It means that this much level of trait is actually required to solve this item correctly. Okay, that's why we are taking the 0.5 location here on the y-axis. Okay, so if we want an item, a person to answer this item correctly, then this much amount of trait is required. So this shows us, this actually indicates the difficulty level of the particular item. Okay, again, the discrimination level of any item is indicated by the slope of the curve. So this slope, as you can see, this straight line, you see it actually shows the slant of the slope. Okay, the steeper it is, it means that the more discriminating this particular item is, and the flatter it is, shows that the less discriminating this particular item is. So ideally we want it to be a steep one. Okay, means that it will be, this particular item then will be able to discriminate among individuals having a lower trait level and a higher trait level. So since this particular item is located here on the trait level, it means that this particular item is able to discriminate among those who are lying on the left hand side of this particular location from those who are located on the right hand side or on the continuum. Okay, so that's how we find we can take a look at the S-shaped curve, and we can see that what is the discrimination level of a particular item. Okay, that's the second parameter. And the third parameter is the pseudo guessing or guessing parameter. So this guessing parameter, how is it indicated in this particular item information curve? We call this item information curve. So here you can see that this S-shaped curve actually started from here instead of here. Ideally it should have started from here, right? But it is starting from here. Okay, where the probability of giving a correct response is like 0.18 or something like that. Okay, so it means that, okay, the person, all those people who are answering this question, okay, those people who are having a very low trait level, okay, ideally they should not have been able to answer this item correctly. But we are seeing that even those who are having a very low trait level, they are also having a 0.13 or almost 13% chance of answering the item correctly without just knowing, just guessing, randomly guessing. They are able to answer it correctly. So that actually indicates, this line is indicating the lower asymptote of the curve, and this indicates the guessing parameter or guessing level of this particular item. So here it is 0.13, and we have certain criteria, like it can be, it is accepted till like 0.34 or 35, it is accepted. Beyond that, if the guessing parameter lies, so for example, for a particular item, the guessing parameter, if you find that it is like 0.5, then definitely you have to either modify it or you have to reject it, because it is not acceptable. Okay, so what happens if the guessing parameter is too much? Guessing parameter too much means the item becomes too easy for the people. So it will not be able to discriminate among the individuals having a higher trait level and a lower trait level. And also, you will see that most of the people will be able to answer it correctly. So it is of no use. This particular item then becomes useless in the particular test, okay, which you are considering. So that's about the S-shaped curve that you are seeing. Not able to close it. Okay. So A represents the item discrimination level, B represents the item difficulty level, and C represents the guessing parameter for dichotomous item. Okay. These are some other depictions of the discrimination and difficulty level. Here also you can see that for 3 items, it is considered difficulty level, all of them having difficulty level of 2.0. And the discrimination level is actually differing. For the first one, the continuous black line which you are seeing, it is +2, okay, which is a good one. For the second one, this dotted line, it is -2. So this is what we call the inverse, inverse curve or negative discrimination index, and it is not acceptable. If you have negative discrimination index, you need to reject that item immediately. Can anyone tell me why? What do you see here for this inverse curve that you are seeing here for a negative discrimination? What do you see? Why should we reject it? Anyone? You can try to answer.
And as the ability increases, the probability of correctness decreases. That way.
Right, very good. So what we are seeing here is that this is going against the assumptions of IRT. So and it is becoming something which is not possible realistically. So this inverse curve, if we are seeing what we are seeing at this level, okay, when the for those who are having a very low very low trait level, they are all of them, they are having 100% chance of answering this item correctly, okay. And when you are considering all those who are having the highest trait level, for them the probability of getting this item correct is 0. Right. So this is going against the logically possible, response pattern in any particular testing. It is not possible. Right. So that means that there is something which is, vigorously wrong with this particular item. And that's why if you are getting a negative discrimination index for any particular item, you should be rejecting it immediately. Okay. The third one you are seeing here, the discrimination with this small dots, okay. Here it's a very flat curve that you can see, a very flat one, not steep at all. So the discrimination is coming to be 0.5, which is quite low. Okay, so that's how you can just take a look at in these different curves and try to understand that how each of these items are actually behaving, right? Some more examples. So you can see item information curve. The item information curve here actually shows the total amount of information that you are getting about the latent trait level from each of these items. Okay, so the previous one that we talked about, the item characteristic curve, tells you about one single item. Okay, here also you get information about each of these items, but it tells you, this item information curve, what gives you additionally is that the total amount of information one particular item is giving you along the entire continuum. So this entire continuum ranges from -4 to +4 theta level, right? And when you are trying to see, plot each of these items on this entire theta level, how much information you are getting at what point. Okay, so for example, here you have 18 items, okay, given on plotted here. So this particular item here, I hope all of you are able to see the cursor moving. So this particular item here is actually giving us the maximum information among all these 18 items, and that too at this particular level around -2. Okay, again it is giving you a lot of information here around around plus 0.5. So it means that people who are lying on this at this region of the continuum, they are for them this item is most suitable. Okay, so this item is discriminating very well at this particular level, at -2 level, okay, trait level, and again at plus 0.5 level. Okay, and again you can see that this item here, this is I think item number 8. It's a very flat curve that you are seeing, the lowest one. So it is not giving you much information anywhere. Right. So by taking a look at these item information curves, you can directly compare each of these items together, and you will be able to get a very clear idea about which item is giving you more information. At what level you are lacking information. Ideally, you should be getting information across the entire theta level. But here, as you can see, at the upper level of the theta or the trait level, upper end, the right hand side, you are not getting much information. So maybe a researcher can try to include some difficult items here so that more information can be obtained at the upper end. So that's how you can make adjustments by taking a look at into this particular curves. Okay, some other examples. The third type of curve that you see here is the test information function, which gives you the information curve for the whole test taken together. Okay, so ideally we want a test which provides good coverage of the wide range of latent ability levels. Otherwise, the test is only good at identifying a limited range of ability levels. So this also gives us a very good idea about how many items are giving you information at what level. But it can be tricky one. Okay, sometimes it happens that you get very good looking test information function, but actually the items might be creating some problems, okay, if you are looking at it individually. So that's why the interpretation of test information function is actually dependent on a number of other factors, right? Coming to the IRT models, we have so far, these are the models which have been developed, okay, for dichotomous responses, means for correct and incorrect responses. You have 3 different models. The first is the Rush model, the basic model, or the one parameter logistic model. There is a very subtle difference between these 2 models, but more or less the same thing. And for the same data set, you will see that both these models actually give you the same, exactly same output. So the Rush model or the one parameter logistic model, you have the 2 parameter logistic model, which considers 2 different parameters, and the 3 parameter logistic model, which considers all 3 parameters. We will discuss these in detail. Yes.
Good afternoon, ma'am. Lovely this side. Ma'am,
Yes.
what is the meaning of dichotomous and polytomous?
Yeah, of course. Dichotomous means where you have 2 different response types. So it can be either 0 or 1, either incorrect or correct. Okay. And polytomous means when you have multiple response options, as in rating scale. I think someone was asking that, what do we do for such kind of responses? In rating scale, ideally we have like 5-point rating scale or 7-point rating scale, 9-point or 11-point rating scale. So you have like multiple response options. So that's the polytomous responses. There we do not have correct or incorrect response. You get only the typical response for a particular person, right? So for such kind of responses also, we have 5 different models which are available: the partial credit model, the generalized partial credit model, graded response model, rating scale model, and nominal response model. Yes, any question?
Ma'am, thank you, ma'am. Got
Sure.
it.
Okay. Any other question? Okay. So we have all these different models available. These days, you will see that a number of extension of these models are also being developed. Constantly, the psychometricians, they are working in producing extensions of these models. But these are some of the basic models that we have. Okay. So the IRT models for the binary responses, I don't think we have much time, so I will not go for the demonstrations. I'll just talk about the basic concepts of these IRT models for binary responses. The 1PL model assumes the discrimination value to be constant. So if you are applying a 1PL or a rush model on a set of data, you are just considering the item location parameter, not the discrimination parameter or the guessing parameter. Okay. The 2PL model or two parameter logistic model, on the other hand, estimates both the item difficulty or location parameter and the item discrimination parameter. So you get output about the location of an item on the continuum and also the discrimination level, right? The 3PL model or three parameter logistic model actually includes all three different parameters. That's the item location, that is the difficulty level, the discrimination level, and also the guessing parameter. Okay. So 1PL model or rush model is the same equation that we just derived in our discussion today. Very subtle difference between 1PL model and rush model. The basic assumptions are all same. Just in the application part, you will see that there is a little difference between two. For example, for rush model, you can apply it on a smaller sample size, like 30 or more is fine. But for a 1PL model, you need to have at least 200 individuals as per Downing in 2003. So otherwise the results can be erroneous. So that's it. But for if you are applying it on the same data set with a considerable number of individuals, you will see that you get the same output, right? So I think you already had a class on R Studio. So I will share the R scripts with all of you, and you can run it on your own. Okay. So these are some of the outputs that you get here. Fitting this IRT model on a dichotomous data set, you get this type of an output where you see that the difficulty levels are given. Since it's a rush model that we are fitting, you get the difficulty levels or the location parameter of each of these items. Okay, there are 8 items, and the discrimination is taken to be constant for all these items. So it is 0.720. That's a constant value taken together for all these items. Okay, all the 8 items. And you get lovely looking, beautiful looking curves in IRT, which tells you, it's the same thing: item characteristic curve, item information curve, and the test information function. Okay, for all these. This is where we are applying the 1PL model. And here again, you will see that if you compare the output estimates, you will see that both the 1PL model and the rush model, it gives you the same, exactly same data. Okay, and the discrimination index also, here you see it's again 0.720. Okay, same for all the items. Here also you get nice looking plots. So the R scripts will be there with you, and you can just run all those R scripts, and you will get all these curves. Okay. There are a few concepts that you need to know while trying to fit the IRT models. You can have IRT fitting these IRT parameters. There are different ways through which we do it. Sometimes we do it using a likelihood, maximum likelihood modeling. Sometimes we do it using a conditional likelihood modeling. So any of these you can use depending upon your requirement. Okay, so here also you get an item difficulty parameterization. Okay, item easiness parameterization is essentially the same thing. You can get the person parameter. What is this person parameter? So for each raw score, you get the estimate. It's like the true score for each raw score, which means that, for example, here, all those test takers who gets a total raw score of 1 has an estimate trait score of theta is equal to minus 2.077. So using a person parameter curve, you can directly plot this raw scores, and you can get an equivalent true score or true estimate of the trait level using this person parameter function. Okay, so you can have this type of plots for checking your items as well. These are the we call these the model based curve. The first one, the items which you are seeing on the upper hand left corner, these actually indicates the model based curve estimated, and the lower ones, these small dots which you are seeing in the lower curves, those dots actually indicates the empirical ICC, empirical item characteristic curves. So what we check here is that whether the empirical ICC is fitting well with the model based curve or not. Okay, so how do we check? If you get an identical shape, then you can say that there is a good fit. If it is not, then it is not a good fit. So this good fit is important because it will tell you that which item is fitting well in your test, which is not. Okay, so person parameter estimate, the one we just discussed. So for each of the raw score, you get the person parameter level or theta level, and you can directly compare people. So for example, someone who is obtaining a score of say 2 and someone who is obtaining a score of 3, although there is physically on the basis of the raw score, you can say that there is a difference of 1 unit in the raw score. If you locate the same two individuals on the theta level, you will see that the difference is not much. It is something like -1 theta level for a raw score of 2, and for a score of 3 it's like minus 0.5 or something like that. Okay, so the difference is not much as per the trait level. So that's how you can compare individuals directly. Okay, we can also get a person item map, which shows that how how the items are, whether the items are well distributed across the entire trait level or not. So ideally, all the items should be distributed along the entire trait level, meaning that the items are able to assess all the the entire range of the trait level. Okay, so here, as you can see, the item 1 is located on the left hand side, left hand panel almost, and all the other items are located close to each other, right at the middle. But there are no other items on the right hand side or left hand side, so it is definitely not a very good representation. So this person item map is actually very important when you are trying to find out whether all these items, they are able to assess the trait level among a large number of people. You are administering it to a large number of people, a bigger group. So where you ideally should be getting a curve where the all the items are well distributed across the entire range of the trait. Okay, you can check goodness of fit using the likelihood ratio test or Wald test. So there are different interpretations here, and we check the chi-square value and the p value. So we want it to be insignificant p value. If you get a significant p value, it means that the goodness is not fit is not good. You need to have a insignificant p value, which actually shows that there is a good fit or not. Okay. Wald test also gives you a check of the goodness of fit in terms of the parameter invariance. So we need a insignificant p value here, which will tell us that whether the parameters are invariant across the different groups who are taking the test or not. If you see that if you see that the p value is significant, for example, here you can see for item number 1, the p value is significant. All right, so it means that the item number 1 is actually dependent on a number of demographic factors. It can get affected by demographic factors there. Okay, so this is something which again gives us a goodness of fit check for such kind of items. Okay. Right. So this is again a graphical check of the goodness of fit. For LR test, you get something like this. So you can plot all these items, and if you see that all these items, as you can see here, except item 1, all the other items, they are having a circular, representation here, overlapping with the straight line. It means that all these items are fitting well, but for the item number 1, it is not lying on this particular straight line, so it actually shows that this item is not fitting very well with the rest of the items. So item number 1 is not actually working fine. So these are some of the estimations of the goodness of fit. We also check the in-fit outfit statistics for getting a very detailed understanding of whether each of these items are working well or not. Okay, for the 2PL model, again, you can fit the IRT, this 2PL IRT, and let me tell you that most of the time you will find that the 2PL model fits way better than the 1PL model or the 3PL model, because 1PL model, those are oversimplified ones, not giving you any indication of the discrimination levels of the items, and the 3PL models are quite complicated. Okay, so it always better to go for 2PL models where you get both the difficulty level and the discrimination level indices. Okay, so here you can see that you get the discrimination indices for all these items, the same 8 items. Okay, and also you get the total information for all these 8 items taken together, which is 94.3%. It's quite high. So it actually indicates that all these 8 items taken together gives you 94.3% information about the trait level, in entire trait level. You get this kind of curves. Okay, but if you look at it clearly, carefully, you will see that some of these items are actually showing inverse curves, meaning that the discrimination is negative. So the items are actually not working fine. You need to reject. You can compare 1PL versus 2PL and compare the log likelihood ratio. So one with a smaller one is actually a better one. 3PL model, here we considered the guessing parameter as well. So this is again output of the 3PL model. So I fitted it on a particular data set, and here you see that if you look at the output, you will get 3 different columns: difficulty level, discrimination level, and the guessing parameter as well, right? So among all these, there are 6 items in this particular data set, and you see that for the guessing parameter, there are 2 items which are having a very high guessing level: item number 2 and 4. So item number 4 is still okay, 0.15, which is within the acceptable range. But if you consider item number 2, it is way higher, 0.53, too high, right? So then it becomes difficult. If you have an item with too high difficulty level, then it's better to reject that item or to check it, okay, and modify it. Okay. So these are the interpretations. The criteria that is given. So item difficulty can range anywhere between 0 and 1. It can go on either side. So at the middle you have 0. On the left hand side you get values which are negative. On the right hand side you get values which are positive. So negative value means easier items, positive value means difficult items. Okay. For the item discrimination, it should be more than 0.5. 0.63 to 0.1.63 is considered to be medium discrimination, and above 1.34 is considered to be large. Guessing parameter cutoff is 0.35. Okay. Interpreting the curves is I have already discussed, so I'm not going to the details. Quickly, I'll just discuss on this polytomous responses IRT models. We have these 5 models. So we start with the partial credit model, which is actually a polytomous equivalent model of the Rush model. So Rush model or the 1PL model, this partial credit model or PCM is actually an extension of this Rush model or the 1PL model. Okay. So here, instead of the item characteristic curve, we get the category characteristic curve. Okay. So here, instead of one single curve, you get 5 curves. If you have 5 options, you get 5 curves. If you have 7 options, you get 7 curves, like that. Okay. So for example, here we have 5 options: almost always, mostly, sometimes, rarely, and never. So you get these 5 different curves. The first and the 5th one is always open. Okay, because on the either side of it, it is not, it's an open-ended option. Okay, so that's why these 2 curves are open, and the middle 3 they are closed because they have proper boundaries defined. Okay, so the PCM is the simplest type of IRT model for polytomous responses. When you have a rating scale with a number of response options, you can apply the PCM. If you want to just look at the discrimination you are not interested into, you are just looking into the difficulty aspect of it. Now one might ask that for a rating scale, what does this mean? It doesn't have any difficulty level, isn't it? In dichotomous responses, we can consider the difficulty level. An item can be difficult or easy, and based on that we can make a decision. But in a rating scale, there is nothing like a difficulty level. So what is that, right? So in a rating scale, when we are considering a rating scale, it is not the difficulty level that we are considering. We are considering the probability of endorsing a particular response option. That is what we are considering. Okay, so if you have like 5 different response options there, out of those 5 different options, okay, for example, here you have 5 options. Out of these 5 options, which one is having the highest probability of getting endorsed by the individuals, okay, or the respondents? So that is what we are considering. Okay, so GPCM an extension of the PCM extension. So in dichotomous items or dichotomous responses, we have 2PL model. We can use a 2PL model. For polytomous responses, we can use the GPCM or the generalized partial credit model. Okay, so GPCM is applicable for rating scales. PCM and GPCM, if you apply on the same data set, you will get that you will see that most of these are, it will give you similar type of responses. Okay, similar type of outputs. So that's the output of PCM. And here you can see that you have the discrimination index is taken to be 1 for all the items. You have 10 items here, and the category this category 1, 2, 3, 4 actually shows the boundaries, okay, which are different for the options. So since we have here 5 options, you get 4 categories. Okay, four boundaries for these 5 options, right? And the discrimination on the other hand, if you look at outputs of, you see that here you are getting a proper discrimination index for each of these items, right? So here again you are getting this first 4 columns indicating the item location parameter, the probability of endorsing a particular category. But again, you are getting the discrimination indices for all these 10 items as well. Okay, so that's the difference that you see. Graphs essentially the same one, just you have to look into whether there is any redundancy in response alternatives or not. Sometimes it happens that, here you can see redundancy where you see the same trait level is being covered by first response option, second response option, like that. Okay, so what is happening here is that what you are seeing here is that there is a redundancy between the first response option and the second response option for this particular item. So what does it mean? Actually, you could have just considered 4 response options instead of 5. So sometimes it happens that you are considering 5 response options, but for your participants, all these 5 response options are not required. 4 would have been enough. You didn't know. Okay, and finally, when you are actually getting the data, you are seeing that, okay, maybe most of them actually ignored the first response option. None of them actually selected it, or very few people actually selected option 1. Okay, the first response category, and all the other response categories were mostly selected. So if that is the case, then it's a burden. It will actually introduce redundancy in the response alternative, and it will actually bring down the discrimination index of the entire item. Okay, so this is something that you should be looking at, and these graphs actually tell you very nicely whether there is redundancy or not. Okay. That's the GRM, or the graded response model. It's similar to GPCM, and it is applicable to 2PL model. It's an extension of the 2PL model. So you get the discrimination index and the probability of endorsement. So essentially same thing. You can apply it for Likert scales. GPCM and GRM, it gives you more or less the same type of output, but just that there's a very subtle conceptual differences between these two models, which it doesn't really matter a lot when you are interpreting the results. So here, instead of categories, you get extremities. Okay, but you also get the discrimination values for each of these items. Okay, and the graphs are also similar looking. You can compare the GPCM and GRM, and you can check whether which of these models is actually fitting well to your data. Depends upon the data that you are taking. It there is no hard and fast rule that you have to apply GPCM or GRM for a particular set of data. Okay, the rating scale model, or RSM, it is similar to the PCM. Okay, and again, it's like a 1PL model. So you get the probability of endorsing a particular item, but the discrimination is taken to be constant here. Plots, again, the person item map, as we discussed for the dichotomous responses, you get the item fit statistics as well, interpretations being the same. And you can there are very specific situations where you can apply the RSM, and you can apply the PCM, although both of these models can be these are like 1PL model, and you can apply it on rating scales, but rating scale model you can apply only if all the response categories are same. So for example, the first one, as you can see, for the first one, first questionnaire that you are seeing on the left hand side, all the response options are same, right? So strongly disagree, somewhat disagree, neither agree nor disagree, somewhat agree, strongly agree, and it's the same for all the 15 items which are shown here, right? So in such a case, for that type of a format, you can apply the rating scale model. But if you have a scale like the second one, okay, and here you are seeing that, for example, the first item, if you consider being able to concentrate on what you are doing, you have 4 options: better than usual, same as usual, less than usual, much less than usual. The second item, if you consider lost much sleep over worry, the options are completely changed. Not at all, more than usual, no more than usual, rather more than usual, much more than usual. Okay, so each of these items is having their own response categories. So if you have a scale like that, then there you cannot apply the rating scale model. There you have to go for the partial credit model. Okay, so that's the uniqueness of each of these scales. Finally, the nominal response model, and as the name suggests, the nominal response model was actually developed for applying it on nominal categories. Okay, so there can be an example like an item for assessing panic attack can be like, you are most likely to experience a panic attack. Option 1, you are with your family. Number 2, you are in school. Number 3, you are alone on the street. Number 4, you are sleeping at home. And number 5, after a fight with your parents or friends. So in this type of an item, there are no rating categories, and you cannot really, place all these options one by one on a scale. So all these are nominal categories, right? So in such a case, you cannot apply any of the other models that we just discussed. So you have to go for a nominal response model in this case. And outputs are similar, but the interpretations are a little different in this case, where we focus on the slopes and the intercepts instead of the boundaries and the extremities. So you get, curves like this, but these are not essentially the same as the item characteristic curve that we discussed earlier, right? So yeah, so this is something that I discussed. So the partial credit model and rating scale model you can use if you are just interested into the endorsement probability of endorsing a particular item or the difficulty parameter. But PCM is applicable only if the scale has its own rating scale structure, and RSM or rating scale model is applicable if all the items are having the same response categories. Okay. GPCM and GRM both are applicable for Likert type data. So you can apply both, and you can just compare the results, and you can choose any one of those these models for your data. And the nominal response model is applicable if your response alternatives are nominal in nature. So I'll stop here, and thank you for your patient listening. If you have any question or doubt, please feel free to share. Yes, any question or doubt? I'm going to share the our scripts with all of you, so you can apply these our scripts on the data which will be provided. So you can run each of these models on your own and try to find out how the outputs are differing. All right.
Okay, ma'am.
Okay, ma'am.
Okay. Any other doubt or question if you have?
Good afternoon, ma'am.
Yes.
Ma'am, how does the guessing parameter work, ma'am? Like guesses, it will be mostly wrong answers, but how does we define what is a guessing parameter, or how do we calculate the guesses? Because item difficulty and item discrimination I was able to figure out, but guessing, I know that it is item response theory's unique function to identify the latent, right? But how does we actually measure it or something?
Yeah. So guessing parameter actually comes into play when you are considering any ability test or achievement test, something like that. So it is possible, you see that if for an item, if there are only two options, okay, can anyone tell me what will be the probability of giving a correct response in that case without knowing anything, just through guessing?
50% maybe.
50%, 0.5 probability,
yeah,
right?
Yeah.
So if you have like 3 options, what will be the guessing probability?
Point 33.
0.33. Very good. So as you go up with different options, the guessing probability actually goes down, right? So what is this guessing probability then? Without having any knowledge, when the person is able to just guess the answer correctly, and by chance it is getting correct, right?
Okay.
So the basic idea in test construction is that we need to reduce the guessing ability as much as possible for one single item, right? Now in classical test theory, it is very difficult. You can do it, but it is very difficult to actually assess the guessing probability. Okay. But in IRT, it has this unique feature where you can actually estimate this lower asymptote of this S-shaped curve, and that gives us a measure of the guessing probability, which if found to be more than 0.35, then we can actually reject the item as it is becoming too easier for the respondents. Okay.
Okay. Okay. Thank you.
Sure. Any other question or doubt? Okay. So thank you all for your patient listening, and I hope this lecture actually helps you in your um, uh, test development practices. Okay.
Ma'am?
Yes.
Ma'am, like for example, if we are having any kind of client, those on whom we are conducting some kind of test, so for for interpretation, for exact scoring, we need some time. What if we are not having like if like for example, if I'm doing counseling to on some person, and if I am not having ample amount of time for getting the exact interpretation and scoring, then in that case, if I use that back depression inventory on that particular client, so in this I just wanted to ask, in short span of time, how to go for exact scoring, because we need some time for scoring, do the scoring.
Yeah. No, the advantage in today's world is that most of these tests, even BDI, the second version that was developed. If you go to the manual of BDI, you will see that BDI, while developing the second version, they used IRT approaches. Okay, so the first version, the original one, was developed using classical test theory. But later on, when it was revised, the researchers, they used IRT for revising it. And there's also a concept that we say that we term measurement invariance. Okay.
Hmm.
So measurement invariance can be tested using confirmatory factor analysis. So that one actually helps us to make sure that all these items, if a test is having measurement invariance, it means that the test items can be applicable to any person coming from any different background. Okay, and you do not have to worry about the true score or the whatever score the person is getting. You can directly compare the observed score across different individuals. So thankfully, all these tests that we are developing these days, and which have already been revised, the classic ones which have been revised in the last few decades, they have been revised using IRT, making them compatible across all the different participant groups and cultural groups. So even for BDI, suppose if you're using BDI, you can go ahead with using BDI2 without any kind of worrying, because BDI2 has measurement invariance already established. Okay.
Okay, ma'am.
Sure.
Okay, ma'am, got it, ma'am. Thank you so much.
Yeah,
Thank you.
I have.
Anything else? Yes.
Ma'am, I saw in your slide that the person who has a high ability and a low ability both has a high standard error, and the person who has a moderate ability has a low standard error. Why this happen?
High
Like
standard
the
error where?
ma'am, a person who has a high ability and person who has a low ability has a high standard error in compared to moderate one.
Where did you see this?
In one of your slide, PPT.
Okay, the outputs.
Yeah.
All right. So in the outputs, the standard errors which you are seeing is actually not indicating the people who are having a higher um, higher anything like that. Okay, this standard indicating something else. It is basically of a particular item. A higher difficulty level or a lower difficulty level, for those the standard error is being displayed here. The interpretations are actually different.
Okay.
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 Yeah. Anything else?
No, ma'am, got it.
Okay. So thank you so much. Thank you again. So over to you, sir.
Thank you, Dr. Sumana Datta, for giving your valuable time to illuminate the most difficult and most relevant topics of the advanced applied psychometrics, that is the IIT model. And you know that is the Indian Statistical Institute is regularly providing different types of workshop and training for educating people about the advanced techniques. Despite of your very busy schedule, Sumana, you have managed your valuable time for us. And I have observed that is all the students, they are paying very much attention to all your deliveries. I hope in future they will apply IIT model in their research. So thank you, Dr. Datta, for your giving precious time to us. Now it is the lunch time. Please go for the lunch. We will meet at 2 p.m.
Okay, sir. Thank you.